make this project very clear how to proceed.
I emailed you this document a few minutes ago, so if you log in, you'll see it. Okay.
Wait, I can't see any of the screen.
Huh?
I can't see the screen.
Tap on the screen, Mark.
I am.
You can full screen it. Top left.
No, she was on.
Yeah.
Wait. I got it.
You got it?
Wait, no, it's
Zoom in.
no, wait.
You can zoom in.
Alright, that's not.
Oh, I'm back. Yes.
But how do I can get rid of this.
You press
yeah.
the top left corner thing. It was like right below that, yeah. And you can choose no thumbnails.
No thumbnail.
Hide,
Yes, I'm like
hide
the
side.
thumbnails.
Alright.
It would be hide sidebar.
So we can have
So
it.
you guys can see it later.
We have it on our computer, so.
No, we're recording what he's gonna
So
say.
that helps a little, but we can't get a bigger picture?
Yeah.
just
Oh, you're gonna, but you're gonna want it. I'm telling you, you're gonna need it later. I'm telling you.
No. This?
It's also like for future classes.
Wait, no, that's what he said last time.
No, but then you can zoom in after that. So you can.
Wait, I lost it again.
Horizontal. That's not good.
Wait, just hold the window down, like the side of the window. Yeah.
Oh my goodness.
Why can't we get the full thing?
Wait.
Push the green button. The
No,
top.
that's when it gets really
You can
small.
zoom in after.
Oh, never mind.
No, it's just.
No, if you push the green button and you go in the top corner,
Yeah. That's
Yay!
For a while.
Alright.
This is on tape. All of this.
Alright. So,
You're on.
you're just.
That's not.
We're going to go back to.
Wait, guys, everyone quiet. I can't hear what
to
you
the
say.
very beginnings of the vertical difference method, where we just compare coefficients, basically. And then you're going to write code to solve the system that arises from comparing coefficients of like terms in the vertical difference method. And then you're going to write code to differentiate and sketch the graph of a polynomial based on that. Right? So I want to take you through that whole process. So you start, this is a little blurry, strangely, but anyway, you start with f of x equals, say, 2x cubed plus 3x, that's my example, and we want to find the derivative at 1. So, you know, the vertical difference should be x minus 1 squared times q, and it's also f of x minus mx minus b, and we're used to comparing and saying, okay, f of x minus mx minus b has to be x minus 1 squared times q, right? But here, I'm going to change things around a little bit, and I'm just going to say f of x is v of x plus mx plus b, which we did when we talked about the definition of the tangent line, if you recall, right? And then, since v of x is x minus 1 squared q, we can write this as x minus 1 squared times some q, and I'm writing q with little q's, suggestively. Now, and so this is my capital Q of x here, and then plus mx plus b. And then I'm just expanding. So is that clear, what I'm doing? Yeah? All right. And then I'm going to equate coefficients. The reason I'm using Q is because we don't really know the degree of our polynomial, so if it was, instead of being degree 3, if it was degree 7, then we'd need a whole bunch of letters, and if we call them all the same thing, just q sub 0, q sub 1, q sub 2, q sub 3, and so on, it becomes easier, and the polynomial, what do we call it, polyfun, is set up nicely to deal with creating a polynomial like little q, or capital Q actually, with little q's as coefficients. So we equate the coefficients, and we get this. Okay, so I'm writing it in a particular way, and notice that in class we always did x cubed, x squared, x and 1. Here I'm reversing that, right? And you should too. Okay, so first the constant, then the linear, then the quadratic, then the cubic, and you get this system. And I lined it up, and you could back solve now if you wanted to just solve it by hand, and you could say, oh look, I know q1. q1 is 2, but then I know q0, and then I know m, and then I know b. So from the bottom up, it's called back solving. Good? All right.
I have a
Oh.
question.
How do I?
You press the arrow key now.
Arrow key now. Okay, yes.
Why do you want us to go like the coefficient and linear? Is there?
Because the matrix you're going to get is going to be nicer.
Okay.
That's why. So now I'm rewriting that system as a matrix. Okay, so let's go back for a second. Why doesn't that work?
Is the other backwards arrow key not working?
I'm sorry, what?
Is the arrow key in the other direction working?
Yes.
It's not working there. That's all.
Okay. Okay. All right. Can you do that?
Yeah.
Does it go the other way?
Yeah.
All right.
Like you have to like do the
Alright. Not used to this. See, here we have this system. Notice it's 1 times b, 0 times m, 1 times q0, 0 times q1, and so on, right? So now, if we look over here, it's 1, 0, 1, 0. And the way you multiply matrices is you take each row and you sort of turn it over like so. So the example that Gordy always likes is, imagine this is a row, and we're pushing it. Can you all see? Okay, that was not. All right. Everyone see the marker? Can you see the marker? Right? If we push it off the table, it falls like that. Yes? And now it's facing this way. All right. So you want to push this marker, which is the top row, off the table, and when it falls like so. And then 1 is going to land, imagine it lands right on top of this. 1 lands on B, 0 lands on M, 1 lands on Q sub 0, and 0 lands on Q1. Anything that lands on anything else multiplies it. And then we add everything up. So what you get is 1 times B plus 0 times M plus 1 times Q0 plus 0 times Q1. Right? And that value goes here. And what we're really getting, let's see if we can go back. Hey. So we're getting 1 times b plus 0 times m plus 1 times q0 plus 0 times q1 equals 0. That's what that top row says. Okay? And then we can, the whole system is right here, and because we wrote it in the way we wrote it, the matrix is what's called upper diagonal. So it has all 1s along the diagonal, which is just nice. Okay? All right. Now you can represent this matrix as an equation. You can call this M, and now this is V, and a matrix that's just one single column is called a column vector sometimes, and then you write it with vector notation, so you put an arrow over it. So we have MV equals F. F is really the coefficient matrix of the polynomial. Remember the polynomial was, what was it, 2x cubed plus 3x squared? Right?
Yeah.
So constant linear quadratic cubic, 2x cubed plus 0x squared plus 3x, it must have been, plus 0. So this is just telling you about f, the function f. So I call it capital F. Right? 2x cubed plus 0x squared plus 3x plus 0. This, on the other hand, this is just the the things that we're trying to solve for. So it's like the vertical, comes from the vertical difference method, so it's v, and then this is m, the matrix of coefficients in the system. Yeah, you can see? Are we good? All right. Notice that f depends only on the polynomial. This really doesn't depend on anything. It's always the same. And this depends only on the point A, where we're trying to differentiate. Okay, so page 3. So I want to just talk about matrices a little. I sort of motivated the use of a matrix because we could rewrite the system in terms of a matrix. Right? It's not clear yet why we would want to do that, right? Just that we can rewrite the system as a matrix. Okay? So what can you do with matrices? Well, here's another matrix. The dimensions of this matrix are 2 by 3. So 2 rows and 3 columns. And this is a row vector. This is a column vector. I'm just giving you some notation here. And you can multiply matrices if the dimensions work. You can also add them, and you can multiply them by a scalar. So I want to just go through those different things. So first of all, if you want to multiply just a row vector and a column vector, this is what I was describing by pushing the marker off the table. You just tilt this over so that it's like this. So A1 lands on B1, A2 lands on B2, A3 lands on B3, and so on, and then you add everything up. Right? And that's how you multiply just one row and one column. If you want to multiply A plus 3B in the upper left, AB times 2, 4 gives you 2A times 4B. Now you do the bottom row times the left-hand column. So that's 1 times C and 3 times D. So you get C plus 3D. And then bottom row times the right-hand column, 2 times C plus 4 times D. All right? Notice that if you want to know what's in, say, the upper right, it's the upper times the right. Yes? So the upper row times the right column goes in the upper right. The lower row times the right column goes in the lower right, and so on. All right? This is just another example. Here's another example. Again, this times this is just 1 times 1, 1 times 1, 1 times 1, and 1 times 1 all added, so you get 4. But if you flip the order, you get this. Because now there are 4 rows and 4 columns, so the dimensions of the product is going to be 4 by 4. You want to know what's in the upper left? It's the upper row times the left column. If we want to know what's over here, that's 3rd row, 3rd column, so it's the 3rd row times the 3rd column. All right? So matrix multiplication does not commute. You can also see that here. This product and this product are different. Right? So the order in which you multiply matrices is very important. Right? Unlike, say, 3 times 4 and 4 times 3, where you're going to get 12 no matter what. Here, this matrix times this matrix is different from the same product in the opposite order. And then, of course, here's a really stark example. The dimensions are even different. This is 1 by 1, this is 4 by 4. All right. So, these matrices here have a very special property. So you can see there's a pattern. It's 1s along this diagonal. So the 4 by 4 case would have 1, 1, 1, 1, and then 6 zeros up here and 6 zeros down here. Right? Those are called identity matrices. And they have a particular property, which is that they don't change another matrix when you multiply. Right? So we could actually check. 1, 0, 0 times 1, 4, 7. 1 times 1, 0 times 4, 0 times 7. So you just get 1 times 1. If you multiply 1, 0, 0 times 2, 5, 8, 1 times 2 plus 0 times 5 plus 0 times 8, 2. And so on. So this matrix acts like the multiplicative identity. So it's like the number 1, but for that matrix. Yes? And you can check it works on both sides. Right? So even though matrix multiplication is not commutative, it is commutative under certain circumstances, and it's certainly, when you multiply by the identity matrix, it's commutative. By the way, I want to mention, here's a good example. This multiplication is defined because there are 3 entries in a row and 3 entries in a column. So when we try and multiply a row times a column, it works. Yes? If we tried to put this over here and multiply, then we'd have 4 entries, and when we turn that 4 entry row, that 1 by 4 row, into a column, it would be too long to multiply 1, 0, 0. So you can't multiply matrices always. The dimensions have to be right. And what has to be right is the row length here has to equal the column length here. All right? Both of these multiplications were defined because here the row length is 4 and the column length is 4. Here the row length is 1 and the column length is 1. So they both work. Okay.
So the number of columns in the first one, it has to be the same as the number of rows in the second.
Number of columns. Yeah, although I would say the row length of the left one has to equal the column length. We're saying the same thing, but I prefer my way. I encourage you to also learn to prefer my way. But yes, that's true. Okay, you can also add matrices. You just add them entry by entry. So you say 1 plus 1 is 2, 2 plus 1 is 3, 6 plus 0 is 6, and so on. So you just add entry by entry. and then you can subtract entry by entry, and you can multiply a scalar, which is just another name for a real number, times your matrix by multiplying entry by entry. So 10 times 1 is 10, 10 times 2 is 20. So multiplication by a scalar and addition and subtraction are very straightforward. It's exactly what you would expect. But multiplication of matrices themselves is this more complicated process that I've now been talking about, right? When you're doing your project, you're going to have to create a matrix class, a matrix object. And then you're going to have to define methods, and some of the methods will be adding matrices. So matrix.add, I think, is how we have it, right? You're going to have to be able to multiply a matrix times a scalar, and also multiply matrices together, right? So I think we have like Trixie is a matrix, and Alice is a matrix, and you can do something like Trixie dot times Alice, and that gives you Trixie times Alice, right? So yeah.
Can you add and subtract matrices with different dimensions?
No. No. So for addition and subtraction, the dimensions have to be exactly the same. It's because you're just adding entry by entry, right? Okay. So that's just all matrix-based basics. Now I want to explain why matrices are useful for solving an equation, right? Because really what we get, or a system of equations. So the vertical difference method leads to a system that you've solved many times, and that can be written as a matrix equation. And we wrote it as mv equals f. So let's go back to a simpler equation, 3x equals 5. Right? So if you want to solve 3x equals 5, you all think, well, let me just multiply by the multiplicative identity, sorry, the multiplicative inverse of 3. So you multiply by 3 to the negative 1. And here I'm multiplying on the left on both sides, just because I now am aware that order can be important, at least in certain situations. Yes? So 3 to the negative 1 times 3x, 3 to the negative 1 times 5. If these are equal, these are equal. But look, 3 to the negative 1 times 3 is 1. And 1 is the multiplicative identity. So I just get x over here. And I've solved my problem. X is 3 to the negative 1 times 5. Right? So you've done that many times. That kind of thing. Well, we can do the same thing with our matrix equation, mv equals f. We think, well, what if there were a matrix, M inverse, the multiplicative inverse of M, so that the product of M inverse and M gives the multiplicative identity? That's just like 3 to the negative 1. It's just like 1/3. Right? If there were such a thing, then we could take this equation, mv equals f, and we could multiply by M inverse on the left on both sides, and then we get M inverse M is I times v, but I times v is just v. So now we found v. We found that vertical difference vector whose entries were b, m, q0, q1, q2. So now we know n, because we know the whole vector v. Right? So this is the big picture here, why we want to, this is what comes from the vertical difference method, and then the reason we want to be able to invert a matrix, which is what a lot of this project is about, is because if we can invert, then we can get to v very simply. Right? Any questions about that? Because that's one of the most important ideas. Make sense? All right. So we have a definition of an inverse matrix here. If you have two matrices, and they're going to have to be square matrices to invert. So if you have two matrices m and n, and their product is equal to the identity, then m is the inverse of n, and n is the inverse of m. And you can prove that if mn equals I, then nm also equals I. So it's going to be a sort of a two-sided inverse. Okay. So now I want to show you how to invert matrices. Okay? Your project, you create a matrix object. You have to be able to do things like fill it with entries. So constructors, I guess, right? Yes?
Very good.
Thank you. And you have to also be able to print it out. So matrix.print. Then you're going to want to be able to add matrices or multiply matrices or multiply a scalar times a matrix. But then you're going to have more complicated things that you're going to want to do. And the most complicated one is to be able to invert. So you want to be able to take a matrix and then have a method that is matrix.invert, and it gives you the inverse matrix. Okay? And then with that, you'll be able to write a method that does the vertical difference method, right? And so the final goal of the project is to use all of this. You input a polynomial, and then the computer sketches a graph of the derivative. And it sketches a graph of the derivative by just picking 1,000 different values for a and finding the slope of the tangent line, the derivative at a for each one, and then it just plots that, right? Okay, so how do we invert a matrix? Well, there are these different elementary row operations. EROs are elementary row operations, and there are 3 of them, and they're just what you use when you solve a system. So suppose that, yeah, well, first of all, if you have 6x plus 7y equals 4 and 7x plus 8y equals 3, you might want to rewrite it. Say you're going to subtract one equation from the other, and maybe you want to subtract the top equation from the bottom. So it's weird to have the top equation on the top if you're subtracting it from the other one. So you might just flip them. That's called switching rows. And it doesn't change the solution set, right? And I bet you've done that in the past once or twice, where you just rewrote your system so that what you had, something that wasn't on the top was on the top, because it was more convenient. All right, another thing that you can do is you can multiply a scalar times a row. So you're going to have a method called scalar times row that will do this. And so here, if you have 6x plus 7y equals 4, and you felt like it, you could turn it into 60x plus 70y equals 40. And you're not changing the xy that solved the entire system, right? So that's scalar times row. And the last one is adding a scalar multiple of one row to another row. So for example, I could add, what did I add here? I think I took -1 times the top equation, and I added it to the bottom equation. That's kind of like subtracting, right? In fact, it is subtracting. But you can think of it as -1 times the top added to the bottom. And it doesn't change the solution set. You should take a moment, not right now maybe, and really convince yourself that the solution set is not changing under those circumstances. So in other words, if x and y satisfy 6x plus 7y equals 4, and also 7x plus 8y equals 3, then they satisfy 6x plus 7y equals 4 again, and also x plus y equals -1. And conversely, if x and y satisfy this, they satisfy this. It's really because if x and y satisfy 6x plus 7y equals 4, and we take 6x plus 7y away from this and 4 away from that, we're taking away the same thing from both. Right? We're not really changing the fact that they're equal. Okay. So this is called Gaussian elimination, solving a system by doing that kind of stuff. I want to give you an example. So here, I'm solving a system, and this is actually the system we got from the vertical difference method in the beginning of the little talk, right? So I'm writing it both as a system and as a matrix, and over here, I'm writing it as what's called an augmented matrix. So I'm taking the 0, 3, 0, 2, and I'm putting it here, and what I'm not writing over here are any of the letters, B, M, Q0, Q1, or well, that's it. I'm not writing those because those never really change, right? It's like B, M, Q0, Q1, B, M, Q0, Q1. It never really evolves. The only thing that's changing are the numbers in front and these numbers over here. So that's the augmented matrix sort of efficiently keeps track of all that data. So what I want to do to solve this is I want to add, let's see, what I decided to do is I added twice this row. Oh, equation, E for equation. So I'm adding 2 times this equation to this for some reason.
To get rid of the negative.
Oh, up here. This is I did this to this, right? So I have -2q1 and I want to get rid of it, so I add twice this to this, right? That's a natural thing to do. And then what you get here oh, sorry. I added twice this to this, didn't I?
Mm-hmm.
Here. Sorry. Q1 equals 2. I double this, I get 2q1 equals 4. I add it to this equation and the 2q1's cancel, right? And so then I get 1q0 plus 0q1 equals 4. So I change this second equation, this third equation. I left the fourth and the second and the first equations alone. I just changed this equation here to this. But now I claim this system and this system have the same solution still. And then for the matrix, I had -2 over here and it became a 0. Yeah? And then I'm just going to continue doing that. I don't think I want to go through every detail, but it's going to be there for you to read about it. But I'm going to keep doing what you've done many times to solve a system. And then every time I do it over here, it gets reflected over here, right? And here I'm just thinking about adding multiples of one row to another row, or maybe switching rows, or maybe multiplying a row times a constant. You with me still?
Mm-hmm.
Okay. So let's now do that again in a simpler version. Why is that like that? Look, was that the page I was on?
No, that is.
I know, but why does it?
You can see the row.
That's interesting that that's over there. All right, so here I have 6x plus 7y equals 1 and 7x plus 8y equals 0, and I want to solve it. First, I'm going to rewrite it as a matrix equation so you can see it there, right? And I'm also going to rewrite it in its augmented form. So now I'm hiding the xy, but you can see the entries in the matrix and also the entries over here. Because xy just never ever changes, so we don't need to write it. Okay? So the first thing I'm going to do is I'm going to multiply -1 times the top row and add it to the bottom row. So that I wanted to do that so I could just simplify my bottom row. And you just get -6x, so that makes an x, and -7y makes a y, and 6, 7, 1, 1. Good so far? Okay. Now I'm going to take -7 times my second row and add it to the first row because I want to kill off the 7. Right? And if I do that, I just have -x here instead of something much more complicated, 6x plus 7y, right? It becomes -x because I have -7x being added to 6x. Here as well, things evolve. Now it's 1, 1. Oh, I'm over here. So now it's just -1, 0 instead of 6, 7. And then this also evolved, and you can see it happening here too. And over on the right, you could just say, well, how did I get from this to this? Well, I simply added -7 times the bottom row to the top row. -7 times 1 plus 6 is -1. -7 times 1 plus 7 is 0. -7 times -1 plus 1 is 8. Right? So now I'm going to go and I'm going to subtract, I'm going to add 1 times the top row to the bottom to get rid of this x. So I get this. And then finally I'm going to just multiply the top row by -1. So what I now can see x is -8, y is equal to 7. I also have an identity matrix times xy, so that's just xy. So it tells me xy is -8, 7, meaning x is -8 and y is 7. And I also have taken my augmented matrix and turned it into an augmented matrix with an identity over here, right? And you could think of the goal as just starting with 6, 7, 7, 8, 1, 0, and turning it via elementary row operations into the identity and something. And then the something over here, that's our solution. There was a hand.
You just said what I was going to say.
Oh, okay. So, and you can check that -8 and 7 actually works. Should we do that? Like 6 times -8 is -48, 7 times 7 is 49, so 1. And then 7 times -8 and 8 times 7 is going to give you 0. So it really works. All right. Now I want to do it again. I'm not going to go through all the details, but I'm going to start with the same exact system here. Except that instead of having 1 and 0, I'm going to have, oh wait, did I do that with, let me just check. Yeah, we had 1 and 0. Now we have 0 and 1. So why would I do that?
Yeah.
Well, that's an excellent question. So I'm about to show you why I'm going to do that.
Oh, okay.
Okay? But the steps are going to be the same, exactly the same. Add -1 times the top row to the bottom row. This is exactly what I did before, because I'm really just looking at 6, 7, 7, 8 and trying to turn it into 1, 0, 0, 1. That's all I'm doing. So it doesn't matter what's over here. Right? So partly I'm just illustrating that. But when we get to the end, we notice that 7 and -6 are the solutions. So we got down to here. All right, so you can read about that. But look what happens when we combine the two. We really have two matrix equations now. This times this is 1, 0, right? So now, we initially said, look, we want to find the x and the y, so that 6 times x plus 7 times y is 1, and 7 times x plus 8 times y is 0. And then we found the x and the y, they were -8 and 7. So now this is true, and you can check. 6 times -8 is -48, 7 times 7 is 49, so you add them, you get 1. But we also solved this system. And Ethan, you were saying why, right? Okay, but if we put it together, if we put this column and this column together, and we multiply this times this, we actually get the identity matrix. Because just 6, 7 times -8, 7, and that's going to be, 1. And then 7, 8 times -8, 7 is 0, and so on, right? So the reason I did them both is because now I really have inverted my matrix, right? The inverse of 6, 7, 7, 8 is -8, 7, 7, -6, right?
That was my
If you have,
That's crazy.
dimensions
No,
there,
actually,
it's
it's
really
very-
fun.
Finding an inverse is never so easy. There are formulas for the inverse of a 2 by 2 and even a 3 by 3, right? But they're not really that efficient, right? So, but this is definitely one method to find the inverse, and it gets laborious. And in previous years in math class, I've had kids doing it by hand with 3 by 3, so you're never going to have to do that. But the whole idea is to use a computer to do this unpleasant and somewhat time-consuming task.
It just looks like you flip.
All right. Okay, so instead of solving the system the way we did, now with hindsight, what we could do is we could just start with a doubly augmented matrix. So this was like the right-hand side of the system when I was illustrating it 2 slides back or 2 pages back. And then this was what was replacing this when I did it the second time. So why not just put both of them there at once and do the same exact process? So here I am doing it all again, just like I did before. And I'm really thinking, let me just take 6, 7, 7, 8 and do elementary row operations. So switch rows, multiply a scalar times a row, or add a multiple of a row to another row. Let me do all of that to these and turn it into 1, 0, 0, 1. And when I'm doing that, this is going to turn into the inverse, right? That's the key idea, right?
Did you guys get that?
Yeah, that's pretty awesome.
Because what you really have is 2 different equations. You have this matrix times xy equals 1, 0, and this matrix times xy equals 0, 1. And as you do your elementary row operations, this right-hand side turns into the solutions. That's what we saw right over here, that the right-hand side starts, say, at 0, 1, and it becomes the solution. X equals 7, y equals -6. Right? So that's how you invert a matrix. And I want to just now show you a couple more examples. All right? And then you have this document, so you can reread it and digest it, because I think it's a whole lot to fully understand in one 45-minute period. All right? So how do you invert a matrix? You form the augmented matrix, M and then identity, and then you perform elementary row operations to turn M into the identity, and I is going to turn into the inverse. Yeah.
On the previous one, instead of doing 1, 0, 0, 1, if we did A, B, B, C, would the result be the augmented matrix, but with A, B, B, C as like?
Well, I mean, you want to do A, B, B, you want to put A, B, B, C
Yeah.
here. I would put it over here.
Because
Right? If you put it over here, then you're inverting A, B, C, D.
Yeah, CD. But if I'm doing like AB, like you forget about the double augmented matrix, so I just do AB. I get a formula for solving any thing which you set it initially equal to, right? So what would the result be if I did A, B, B, C? Like right now when we do 1, 0, 0, 1, we get the inverted matrix. Would it work for any pair of numbers like that, or was it only
Yeah,
working for
I
0,
mean-
1?
Isn't that a function? Can you put
Yeah,
an input
exactly.
and then you
Yeah.
crank it?
So you want to just put, I mean, why A, B, B, C? and
Because
not-
that's 1, 0, 0, 1.
No, I know, but why not just A, B, C, D over here? You're then solving two systems at once.
But like, would the answer still be the inverse? Like over there we see 8.
No, the answer
Yeah.
won't be the inverse unless
It's
it's 1, 0, 0, 1, because
Yeah.
it'll be the matrix that you have to. You know what it'll be if you do A, B, B, C or A, B, C, D.
Yeah.
Then what you're going to find here is the matrix that when you multiply that times your original matrix, you get A, B, B, C.
Okay.
Right?
Yeah.
So that's not as useful as the identity matrix, but it would work. Not in the inverse matrix. Okay, so here we go. Let's do this with this. 1, 2, negative 1, 0, 3, 0, negative 4, 0, 5. So you form the augmented matrix. Now you do elementary row operations, and I indicated them here. So the first thing I did is I took row 3 and I changed it to 4 times row 1 plus row 3. Right? So you're going to have a method that would do exactly this. And when we do that, when we take 4 times this, the 4 times 1 plus negative 4 is 0. 4 times 2 plus 0 is 8. 4 times negative 1 plus 5 is 1. And then this becomes 4, 0, 1 because we had 4 times 1. Right? So that's the first thing I do. And now I'm going to continue doing these elementary row operations that you can read about and understand in more detail. And eventually I turn the left-hand side into the identity. And the right-hand side turns into the inverse matrix. And you can check it. Here I'm multiplying, and you get the identity. Right?
If, say, we had a matrix, like a 3x3 matrix in this example, where every position like was a number like other than 0, is there like a objectively like effective way to solve the system by like
So
instead of going
what's-
from like up to down or down to up? Or
I mean, that's the challenge of the project, and we can maybe talk more about, good ideas.
yeah.
But you start with this thing, and you have to make choices. I think you're saying, how do you make the choices, right?
Yeah.
For what to do. You have to make choices, and if you're a human being, you just look at it and you go, oh, I could kill off that negative 4 with this 1, right? And so on. But if you're coding, if you're telling the computer what to do, you can't just say to the computer, just make an intelligent choice. Look at the matrix, you'll see, maybe there's a negative 4, maybe there's a 1 above it,
Right.
You have to write an algorithm. So how do you turn this sort of heuristic, somewhat, not well-defined method, you just sort of do stuff until you get to here. How do you turn that into an algorithm? That's the real challenge and sort of what makes it interesting, right? And what you can keep in mind is that when you're looking as a human being, you are trying to do things that will avoid nasty numbers. Like if you could maybe get rid of some other entry, but everything would become over 5, like 4/5 and 7/5 and whatever. Maybe you don't want to deal with that, and you think, I could do something else and keep the numbers whole. Well, the computer doesn't really care about fractions, right? So you can avoid certain concerns that you would have as a human being, but meanwhile, it still has to become an algorithm,
Mm-hmm.
right? That's why this is a valuable coding assignment, right? Because I think that that's something you encounter all the time in computer science, that, there's something that maybe a human being would do, whether it's math or something else, and you have to figure out how to turn it into something that a machine can do, so that there's a very specific step-by-step procedure, right? Okay, so I want to, I have till 10 of, quarter of. Can I go till 10 of, or
Yeah.
I'll leave you in 2 days.
So I want to talk about 2 more things. One is reduced row echelon form, So what is reduced row echelon form? Well, first row echelon form. These numbers 1 and then 2 and then 1 are called pivots sometimes. They're just the first non-zero entries in any given row, right? And a matrix is in row echelon form and not necessarily square matrix if, first of all rows with at least one non-zero element lie above any rows consisting only of zeros, so the 0 rows are at the bottom. Yes? And then the pivot of any non-zero row is always strictly to the right of the pivot of the row above it. So the pivot here is to the right of this pivot, the pivot here is to the right of that pivot. Right? So that's row echelon form. And then reduced row echelon form has a further condition, which is that every pivot is the only non-zero entry in its row. So here's a pivot, and all the pivots are 1. So 1, 1, 1. So I turned this one, well, that previous one was in row echelon form, but not in reduced row echelon form, because we have a 2 here, and a 3 above it, and a 1 here, but a 4 above it. Whereas here we're in reduced row echelon form. Okay? So you can do elementary row operations to put something in row echelon form or in reduced row echelon form. There's always a reduced row echelon form. So if someone handed you this matrix, you could say, oh, let me divide this row by 2, so that's a 1. And then let me add -3 times this row with a 1 in it to the top row. So I'll make this 3 into a 0. And let me add -4 times this to that, and then I'll make that a 0. So you can always, always, always put any matrix you like in reduced row echelon form, and that form is unique. All right? So why do we care? Well, hopefully I said over here, when you form your augmented matrix MI, then the goal is to put that in reduced row echelon form, because if M is invertible, then the reduced row echelon form, maybe I'll write it over here, is going to look like this. It's going to be this, and then something could be over here like a 2, and then maybe a 3 and a 4 and a 5, and a 0 and a 7, and 0, 0, 8. Something like that. So this is in reduced row echelon form. There's pivot, 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 zeros above it, and all that. And look, we've actually turned our M, so it was MI, and now it's become I, so this is going to have to be M inverse, right? So you can interpret your goal now as turn your 3x6 matrix that you were handed, whatever it was, put it into reduced row echelon form. And even if your matrix is not invertible, you can always do this. It's just that if your matrix is not invertible, because not every matrix has an inverse, you just won't get 0, 1, 0, 0. Sorry, you won't get the identity over here. Like you might have 0, 0, 0 in this bottom row. But you can always put anything in reduced row echelon form with elementary row operations. So, well, I mean, it just turns out that there's of course an answer to that. A matrix actually represents a transformation from 3 dimensions to 3 dimensions. You can think of it geometrically. And when that transformation is not 1-to-1, the matrix is not invertible. But much more sort of concretely, if you took, say, 0, 0, 0, 0, 0, 0, 0, 0, 0, there's nothing you can multiply that by to get the identity, right? So there's certain matrices where no matter how hard you try, you're not going to be able to invert it, because it has no inverse, right? So we could talk more about that, but not now. And then last thing, using matrices to differentiate, I just want to take you through this very quickly. So you have your vertical difference method. This is when we first set up the 2x3 plus 3x at the beginning of this. There was a system of equations, and it became this matrix equation. So now I'm just going to invert this. So when I invert it, I first form my augmented matrix. So now it's actually 4 by 8. and I do some simple elementary row operations to get it to here. All right? So now this is my inverse matrix. My inverse matrix is this right here. Okay? So then I'm just checking that it's the inverse. So again, this is my system of equations. I'm going to multiply on the left by the inverse, just like we talked about with MV. Multiply on the left, multiply on the left. And then what you get over here is just the identity times BM Q0 Q1, which is just that. So now I know BM Q0 Q1 equals this times this, and I can even multiply it through. And look, M is 9. All right?
Oh my god.
And so there's one more example, but I'm going to stop there, I think. All right? And so if M is 9, I also know B is -4, and I know my tangent line is 9x minus 4. All right? So that's
Crazy.
Thank you, Gomp.
Hang on one second before you guys go.
So you have the big picture, I hope, now, and you should just find me and ask me questions about the
Do it dramatic.
details of the math, right?
I emailed you yesterday. I'm pretty sure I emailed someone else.
No, you did email.
I emailed you.
Okay.
Right. Should I keep recording this?
Wait,
or-
Gomp, flash an X for the X class, for the video.
And